In this video, we will look at a new take on the good old Matheson reaction. This great synthetic tool allows for the insertion of lithiated dihalomethane into the carbon-boron bond of a boronic ester containing a chiral auxiliary, such as pinene-diol, for example. This generates an alpha-haloboronic ester stereoselectively. Subsequent substitution with a nucleophile usually proceeds under inversion. But we now showed that addition of cheap sodium iodide to the substitution step can allow for the substitution to proceed under retention. And if this looks straightforward to you, I bet you the mechanism is not what you think. As this variation of the reaction gives access to the epimers of the normal Matheson products, we called this process an epi-Matheson reaction. This work has just come out in Organic Letters, and as always, a link to the paper can be found in the video description. Before we go into further detail, let's have a quick recap of boronate homologation chemistry. This super versatile class of reaction provides great tools for the synthesis of complex chiral molecules. And the last 40-something years have seen quite a lot of development. During this time, three principal approaches have been developed. The original Matheson homologation, as we just saw, relies on a chiral auxiliary to direct the insertion of lithiated dihalomethanes stereoselectively, generating alpha-haloboronic esters. Subsequent substitution can be conducted with carbon, nitrogen or oxygen nucleophiles and proceeds under inversion of the newly formed stereocenter. In the 2000s, Agarwal and Blakemore independently came up with new reagent control variants by using chiral carbenoids. These highly reactive species can be generated, for example, by metal-ligand exchange from chiral sulfoxides or stereoselective lithiation in the presence of a chiral diamine. Compared to the classic Matheson reaction, this new approach allowed for conducting homologation reactions more or less independent of any chiral information present in the substrate. And even more recently, Fu and Jacobsen introduced catalytic versions of the Matheson homologation. While Jacobsen targeted the homologation step in order to generate the alpha-haloboronic ester stereoselectively, Fu, on the other hand, managed to make the substitution step enantioconvergent. That means that his catalyst works on a mixture of alpha-haloboronates which subsequently reacts to one single stereoisomer. Looking at this overview, one might see the classical progression to more and more efficient methods. Starting from chiral auxiliaries, then moving on to chiral reagents, before finally arriving at a catalytic method. Well, to a certain extent, this is certainly true. But new developments in chemistry are different from other areas such as mobile phones. While nobody would probably use the old Motorola brick from the 1980s nowadays, the Matheson reaction still is quite popular. And one reason for that is the way in which these reactions are often applied. That makes chiral auxiliaries much more efficient than one might think. And only this year a mechanistically completely new, but nevertheless still auxiliary-based method was published. So why are chiral auxiliaries better than their reputation in this particular case? Boronate homologations are usually applied iteratively to build up larger chain-like molecules. For reagent and catalyst-controlled methods, this requires the addition of new chiral material for every single iteration. The chiral auxiliary, on the other hand, remains part of the molecule and can do its job over and over again. Furthermore, a diol is needed in any case to form a boronic ester, so there is no additional step necessary for attaching or removing the auxiliary. Therefore, especially a cheap chiral auxiliary such as pinene-diol, which forms highly stable boronic esters and is available in both enantiomeric forms, should not be underestimated. That being said, there is an obvious problem with the iterative Matheson approach. Namely, that the chiral auxiliary always directs the newly introduced stereocenter the same way. Chiral reagents or catalysts, on the other hand, allow chemists to choose the configuration at each newly introduced stereocenter individually. So, wouldn't it be nice to have a cheap method that allows you to generate configurationally divergent stereocenters without changing the chiral director? This is exactly the idea that prompted us to develop our new method. Our initial idea was quite straightforward. We wanted to incorporate an additional inversion step by introducing a nucleophile that can double as a good leaving group. For that, we tried several phenolates and thiophenolates. Cutting a long story short, none of these were any good. What did work, however, was adding sodium iodide, which after some optimization delivered decent results for primary and for our Grignard reagents, although secondary Grignards and nitrogen nucleophiles failed. Those who are not regularly working with alpha-haloboronates might not be that surprised by this, as iodide is both a good nucleophile and an excellent leaving group. So isn't it a perfect candidate for our original idea? Well, actually it was a bit of a far shot. Alpha-bromoboronic esters do have a much greater tendency to undergo isomerization than their chloral counterparts. Therefore, we expected alpha-iodoboronic esters to isomerize even faster. And, fun fact, they do. Monitoring the substitution of this alpha-bromoboronate with sodium iodide by proton NMR clearly shows that the epimerization reactions connecting the two iodides is faster than the substitution of the bromide. That's why you see the overlaying doublets of doublets for the alpha-iodoboronic esters grow constantly as a 1-to-1 mixture, while there is still starting material in the mixture. So, we are actually losing the stereochemical information at this point. But nevertheless, we still receive a highly diastereomerically enriched product after substitution with phenyl Grignard. And that means that there must be a somewhat more complex mechanism at work than just a simple double inversion reaction. So let's have a closer look at this substitution step. In most textbooks, you will find that addition of a Grignard to an alpha-haloboronate leads to an 8 complex, which then undergoes stereospecific 1-2 migration. If this would happen in our case, the 1-to-1 mixture of alpha-iodoboronates would lead to a 1-to-1 mixture of substitution products. We therefore suspected some Curtin-Hammett type equilibrium to funnel both epimers to the right product. In order to gain deeper insights into this, we did quantum mechanical calculations, and they do indeed draw a somewhat more complicated picture. Let's start by thinking about the configuration in which the Grignard might encounter our two iodides. Hyperconjugation between the sigma orbital of the Ci bond and the empty p orbital of the boron atom makes these two conformations for each diastereomer particularly stable. Therefore, we actually have 4 different species of iodide in our solution. 2 in which the iodide is on the endo side of the molecule, and 2 in which the iodide is on the exo side of the molecule. When these compounds see a Grignard molecule, our calculations suggest that they don't immediately form an 8 complex. The first thing that happens is a reversible association of the Grignard's magnesium atom to one of the boronate oxygens. Theoretically, this again can happen in 4 ways, as the Grignard can attack both O2 and O3 from both the endo and exo side again. This way, each of the 4 iodides can theoretically form 4 magnesium complexes, which alone opens up 16 different pathways in which the reaction could go. The good news is that all of these pathways show very similar profiles with respect to the rate-determining step. Therefore, let's just compare the 2 which start from the 2 most stable and thus most prevalent magnesium complexes. Those magnesium complexes are predicted to react further to the expected 8 complexes. And the energies for the calculated transition states do suggest that this happens faster for the 8 complex that is leading to the epimetism product. And since all subsequent transition states are lower in energy than the ones leading to the 8 complexes, it is reasonable to believe that this is the origin of the diastereoselectivity. However, these reactions do deliver products in more than 50% yield. Therefore, some connection between the left and the right pathway must exist that allows the formation of the red epimetism product from one of the species on the blue pathway. And here we must give credit to one of the reviewers who kept pushing our nose on this topic. Initially, we took it for granted that this epimerization takes place on the stage of the alpha-iodoboronic ester, since we saw how fast this reaction occurred in the NMR tube. However, the NMR was recorded at room temperature, and this reaction happens while allowing the reaction to warm up from -78 degrees Celsius to room temperature. So, based on the reviewer's suggestions, we did some more calculations, and those showed that this isomerization pathway can't be the connection we are looking for. All isomerization barriers leading from one iodide to the other are predicted to be higher than the ones leading to the 8 complexes. Therefore, continuing on the reaction pathway towards the substitution products would always be faster than switching routes by isomerization. But luckily, there is another species in the reaction that is activated for isomerization, namely the magnesium complexes. Coordinating a formally positively charged magnesium atom to the boronate oxygen increases electrophilicity, and thus epimerization can occur with a lower activation barrier. So, some of the magnesium precomplexes allow for setting up a fast equilibrium, and thus lead to a typical Curtin-Hammett situation. And this funnels the undesired diastereomer towards the epimedicine product. If you're a bit like us and find these mechanistic considerations extremely compelling, or if you want to learn more about the substrate scope of this new epimedicine reaction, check out our article in Organic Letters. In a nutshell, primary and aryl Grignard reactions work very well, while others are somewhat more tricky. One quite interesting result is that all our attempts to introduce alkoxy substituents preferably led to the medicine products, only with less good stereoselectivities. While this throws up some new interesting mechanistic questions, its synthetic use is actually very limited. Fortunately, there are other stereodivergent ways to make glycols. In our paper about a unified synthetic approach to all aldohexoses, we employed strategic solutions to make both erythro and treoglycols. If this tickles your fancy, check out the video abstract for this paper. You can find it behind the link on the left. However, if you plan to finish your medicine sequence with a chiroglycol, you might rather check out our work on the reaction of alpha-haloboronic esters with chirocarbenoids. The video abstract for that work waits for you behind the link on the right. But before you leave for one of those videos or the original article for this video, which is linked in the video description, we want to say thank you. Especially, we want to say thank you again to the really constructive reviewers we had for this paper. Also, the DFG for funding, and of course you for your kind attention.